How are you doing? Here on our University of Michigan campus, great crowd in the room here, and those who are watching our live stream, welcome to Saturday Morning Physics. There's some good news. It's spring. And it was worth waiting 2 weeks from our last event, right, that was deep in the throes of winter. Who was here for that unique, family-friendly event? Many hands going up. That was presented by 15 students, undergrad and graduate students from LSA and the College of Engineering, and the staff, and Spot, the robot dog. If you had a chance to see him, all made that an incredible event. So I'm glad for those who were here, and it was very exciting for the large number of Saturday Morning Physics fans who were here. I'm physics professor Tim Chupp. I'm one of the organizers of Saturday Morning Physics with our team. There includes Carol Raybuck, and we should always give her a great... our gratitude to her, and the team led by Monica Wood of the Demo Lab. She's not here today, but Connor Heaney and Nick Arnold are taking that up from the Warren M. Smith Demo Lab. And as you can see today, they've had quite a lot to do. So before moving on to our program, first I want to tell you about a lecture that may be of interest to Saturday Morning Physics fans coming up. It is called Why We Explore. It is the Lineweber Center for Theoretical Physics lecture, and it is on Thursday, April 3rd at 4 p.m. in Rackham Amphitheater. I also want to note that Saturday Morning Physics is made possible by you, by generous contributions. And we recently had Giving Blue Day, a couple Wednesdays, or last Wednesday actually, and over 50 people contributed explicitly to Saturday Morning Physics. And in fact, we were in the top 10 of, they actually keep track of these numbers, the top 10 of the LS&A, almost 90 organizations and units that raise money. So we're very grateful to the people who are supporting Saturday Morning Physics. And if you want to know more about supporting Saturday Morning Physics, SaturdayMorningPhysics.org will provide you with the information. I also want to note before moving on that we will have a question and answer period at the end. And for those online, or even if you're in the room, you can send your questions to physics@umich.edu. And also we'll have people in the room, we'll have microphones in the room for people who want to ask questions. So now, we are honored to welcome Professor Karl Krushelnick. He's the Henry Gomberg Collegiate Professor and the Director of the Gerard Moreau Center for Ultrafast Optical Science in the College of Engineering here at the University of Michigan. This is the home of the recently constructed ZEUS, or ZEUS. Pronunciation we'll learn in a moment. The petawatt laser, we'll also learn what that means. And that's a facility which he'll tell us about today. Professor Krushelnick grew up in Woodstock, Ontario. I was going to say Woodstock and then Ontario. Sort of halfway from here to Toronto. And he attended the University of Western Ontario and went from there to attain his PhD at Princeton in plasma physics. He has had a number of academic positions at Cornell as a postdoc, at the Naval Research Laboratory in DC, Imperial College in London, where we managed to attract him to the University of Michigan in 2006 to lead the Center for Ultrafast Optical Science and High Intensity Laser Physics. He has numerous accomplishments and he has received many honors, but I'm actually most appreciative that the first thing that he lists is the over 40 PhD students whose research he's supervised, many of whom have received awards and recognition for their PhD research. Karl also has honors of his own, including fellowship in the American Physical Society and the Optical Society of America and the Institute of Physics. So I should note that the ZEUS laser is moving from development and construction to productive science. And so this topic is extremely important and timely for us. And we're very grateful to have Karl here to tell us about it with his title, ZEUS, the most powerful laser in the US.
Okay. Okay, thank you very much for the invitation, and I'm pleased to be here. So today I'll talk about what the ZEUS laser is, and so I have talk about the physics and mostly a lot about the technology of very high power lasers and what we can do with them, and how they're important for science. And so I've had a lot of contributions from other members of the ZEUS team. So I'm coming from North Campus, not too far away, the engineering campus, to, but I also have a connection here to the physics department. I have an appointment in the physics department. Like any professor in University of Michigan, the first thing I do when I'm giving a talk is I type that topic into ChatGPT and see what comes out. So that was pretty good for a first thing. So we have ZEUS here and a powerful laser beam emanating from his eye. And I don't know, that doesn't really look like me, but well, maybe I can work on it. So the rest is not so much ChatGPT, but you'll have to kind of find out for yourself. So I'll talk about lasers. A little bit of background, maybe people might be familiar with what lasers are. They're kind of ubiquitous now in technology. But I'm interested in very high power lasers, and what does that mean? And in particular, the ZEUS laser facility at Michigan, which is just a mile or so away. And what that means in that topic of science and physics is called high field science, and there's various applications. And so just to tell you how we make these lasers, what it looks like, and what the science, what it is and what it isn't, and what the science means. So a lot of superlatives, lasers that are very high power, okay? Not, you're used to perhaps using lasers in a barcode reader in the supermarket. These are much different from that. They're extremely high intensity. And intensity, again, high power means energy divided by time. And so these are typically pulsed lasers. The laser that I'm holding here is laser pointer. It's a diode laser. It is continuous, we call a continuous wave laser. If you take the energy and then squish it in time to make a pulse of light, then that increases the instantaneous power. So I'll be talking about very high power, instantaneous power. And then if you can focus that energy and that power to a small spot using a lens or a mirror, you can create high intensity. And intensity is the thing we're interested in terms of the science, in terms of the physics, and the intensity is proportional to the square of the electric field. So this also means very high electric fields. So how do we get that? How do we get really high power? Well, we make really, really, really short pulses of light. And so the shortest thing that the human technology can devise really is a pulse of light. And we utilize the fact that we can make these pulses of light using lasers and try to pack as much energy as we can into the laser pulse, and then we do our science with it and do applications. And so this is called then high field science. So just background, lasers. So what's a laser? Again, it's an acronym, light amplification by stimulated emission of radiation. Okay, so it's not like normal light. It is typically much brighter and coherent. And so you know that light is a wave. It's a bunch of photons. And so typically, if you have a bunch of photons from a flashlight, for example, from this light, which is much different, this flashlight is much different from the light of this laser, all those photons are just flying around coming from the light source. They're not connected to each other. And so if you have a laser, you have them all at the same frequency, basically, at the same color, and they're all lined up. So they all the waves have the same have the same phase. So the phase of this part of the laser beam is all the same, because you can see how the wave moves, so that this part of the oscillation is the same. And so it's connected in this direction. So this is a laser beam. This is called spatial coherence. So it has the same phase across this direction. And also the phase on different parts of the beam are connected. And so that's called temporal coherence. So lasers are unique in the sense that they are coherent in both time and space. And consequently, that makes them very useful. They're very directional. And they have the unique properties that you can, again, manipulate them in ways you can't do with regular light. So ultra-fast lasers. So I'm talking about really, really short pulses of light, and the shortest we can possibly get. And how do we make those short pulses of light? So if the first thing is, what's a laser? Okay, so the typical thing is it's made in a cavity. So we need a medium in which you get a population inversion and you get gain. So a photon, which is produced in, you excite atomic transition in this material by pumping it, produces a photon, and then that photon can bounce back and forth between mirrors in this cavity and get amplified as every time it goes back and forth. This is called an output coupler, which is a partially reflective mirror, and this is a high reflective. So all the photons that hit this mirror will bounce back, and some of the photons that hit this reflector will come out. And this is the source of the laser beam. So this is what's called an oscillator, the source of the light. So you can see in this case, if I take this as an example of a gain medium, a laser rod, and so this is a material called neodymium doped glass. It's a very common laboratory laser. And so you would take look at two different types, different colors. If I take red, I don't know if you can see this, yeah. A red light, this light should go all the way through this beam, this rod. And if I take a green, oh, it's not green. If I take a green colored laser, this guy will not go through. This is absorbed. So this is what pumping means. So if I want to produce a population inversion in our gain medium, I would irradiate it with green light, and it would produce a population inversion in the neodymium ions that are in this piece of glass. And if you do it hard enough, then you can, and surround it with mirrors, you can get a beam of laser light. However, that's not enough to make a short pulse. We want to make a short pulse of light, and so we need to work that. We need to do a little bit more work. And so the mechanism by which you produce a short pulse is called mode locking. And so you put another crystal inside this cavity, and that controls the different cavity modes. So in actuality, there's not just one frequency that can be produced, not just one wavelength. There are a series of different colors that are exactly matched and produce a standing wave in the cavity that also can have gain inside the material. And mode locking means that we fix the relationship of the modes to each of these cavity modes. So it's a way to obtain these really short pulses. So if I just have a laser that's lasing, that's producing directional coherent radiation, but it's not mode locked, it produces a big spray of photons, which are slightly different energy, but they have different frequencies, and they're not the phases of those cavity modes are not fixed with each other. However, if I can fix them and make them all the same so that they add up together in one place, you can produce a pulse of light. So instead of a whole bunch of photons rattling around inside a cavity, if you can fix the phase of all the different frequencies that are that can be produced, then you can only have one pulse, which is going inside the cavity, and so you can produce a train of output pulses. So in this case, in our case here, if we have one frequency that's lasing, for example, in a CW, a continuous laser, then in time, it's very uniform, right? So there's no variation time, there's no pulse. It's just a very uniform frequency. And has a narrow spectrum, and so it has a continuous wave. So it's like this laser itself has a very narrow spectrum. It's not a pulsed laser. So if I increase the spectrum, have couple more frequency modes, couple the phases of all those modes together, so I'm lasing inside my cavity with many, many different frequencies all mode locked together, then if we add them up because of constructive and destructive interference, we get an output pulse, and that's what we want. And so the trick is to make as many frequencies inside our cavity mode locked together to produce the shortest possible pulse. And so in this case, the frequency bandwidth is called bandwidth nu, and so the time duration is the output pulse duration. So these are the same photons, one's in time and one's in frequency. And so the limit, the more frequencies you get, the shorter the output pulse is, but you also have to lock all those frequencies together to get them to lase simultaneously. So, and that's basically, from signal theory, from Fourier theory, the frequency spectrum is inversely proportional. The width of the bandwidth is inversely proportional to the output pulse you can get. It's the same for acoustics. It's also related to the Heisenberg uncertainty principle for wave mechanics. So how fast is ultrafast? So that's how we make these short pulses. And so the pulses we get are as short as anything human technology can devise. And so how fast is that? So how fast is ultrafast? So 1 second, if I think of a flashlight and I shine it to the moon, it takes about 1 second for the light from the flashlight to get to the moon. If I think of a movie, the different frames of a movie or from your TV set are around 1/30th of a second. Okay, so that's on the order of 1,000 miles or something on that order, thousands of miles, on the order of the Earth scale. The flash of a camera, people who, if you still use camera flashes, last about a microsecond or 1/1,000,000th of a second. Around that time, it takes a few hundred meters. Light can travel in a few hundred meters. 1 nanosecond, 1,000th of a millionth of a second, a billionth of a second. So light, in fact, only travels about 30 centimeters or about 1 foot. So the speed of light is, you can think of it as 300,000 kilometers per second, or we like to kind of think of that being as 1 foot per nanosecond is the speed of light. So light travels about 30 centimeters in a nanosecond. But we want to do better than that. A picosecond is 10 to the minus 12 seconds, a millionth of a second. And that's about the time it takes for a pulse of light to travel across a period on the surface, on a piece of paper. So, and that's a time scale for atoms and molecules. And we can even do better than that. We can go down to femtoseconds. So I'll be talking about femtoseconds. That's the time scale on which we can produce pulses of light. That's the time scale, the shortest thing that human technology can typically devise is on the order of femtoseconds. The physics that happens on femtosecond timescales are like nuclear physics. And light will only travel a couple microns, or less than a micron, on the order of 300 nanometers. So it's very, very short distances. So the kinds of beams that I'm talking about are pulsed beams of laser light. But if you think of them in space, they're really, really thin. They're a flying pancake of light. They're thinner than a pancake, like flying crepe of light, actually thinner than a crepe. So I don't even know how to describe it, but it's a really thin sheet of light traveling through space. So it's a kind of a delicate thing, and I'll mention that as well. So we make these short pulses of light. They're femtoseconds in duration. At ZEUS, our laser pulse is around 25 femtoseconds. But we want to get lots of energy. We want to get high power, and power is energy divided by time. So we have short amount of time, so we can make high power that way, but we still need to increase the energy as much as we can. And so the technique of doing that is called chirped pulse amplification. Okay, so this is where we start with our short laser pulse, and we play a trick. We can't take that pulse and amplify it in a laser amplifier like this, because as it travels, it's very, very short, so it's quite high intensity. As it travels and it gets amplified, then it starts to undergo nonlinear processes, and it'll damage our amplifier. So the trick that we play is to stretch it in time by about 100,000 times to reduce the energy. And so we know, because we have a very short pulse, that it has lots of different frequencies. So we stretch it in time with having the red part of the pulse in front of the blue part, and that's called chirping the pulse. And you can do that just with some things like diffraction gratings. So these are diffraction gratings. They're just grooved like a piece of optics, like a mirrored surface, which has grooves in it. And that actually reflects different wavelengths at different angles, again, because of constructive and destructive interference. And so the path of the red part and the path of the blue part of the light will have different directions. So there it is, but I'll do this. So this is a diffraction grating. So you can see if I take, so it's one way of making a spectrometer, for example. If I take my green light, I don't know if you can see this yet. So it only reflects in one direction. I guess you can't really. It only reflects in one direction, my green diode laser pointer. But if I take my flashlight, which is white light with lots of different colors, it separates all the different colors into different angles. I don't know, sort of. Maybe that looks better there. So you can see the red part and then the blue part of the spectrum. So that's really all we use. In fact, we just use two of these guys to stretch out the pulse by bouncing the pulse from one to the other, and then so they have the different colors have different paths, and so they stretch the pulse in time. And a pulse that is like this, that has frequencies which are aligned in time, is called chirped. So that's the thing we amplify. It has lower intensity, so we amplify as much as we can through this system, and then we have a higher intensity laser pulse, but then that's still a long pulse. So we start out with 25 femtoseconds, stretch it in time by a factor of 100,000 to almost a nanosecond in duration, and then we amplify it, but then we have to go back. We have to squeeze it together, and to do that, we also use a set of much larger, more expensive diffraction gratings instead, and aligned just backwards. So they're facing each other rather than facing away from each other. So this thing is called a pulse stretcher, and this thing is called a pulse compressor, and this is made of, big diffraction gratings that are a couple $100,000 each for ZEUS. So the most powerful lasers in the world now produce powers on the order of petawatts, 10 to the 15 watts. So that's a million billion watts. And so the average power consumption of the US is around about a terawatt, or around the Earth is around 8 terawatts. So 8 times 10 to the 12 watts. So this is on the order of 1,000 times more, or 100 times more than the total energy power consumption of the Earth. However, this the difference between a pulsed source and a CW source, obviously. So this is the peak power of our laser, whereas this is the continuous power on the cross of the electricity grid across the world. There's a lot of interesting physics that's possible with higher powers, and I'll show this. This is a plot of what I just talked about. The laser itself was invented in the early 1960s, and shortly after that, this concept of mode locking, producing ultra-short pulses, was developed. And so this is increasing intensity, increasing possible intensity. And then around 1985, that technique that I just talked about, chirped pulse amplification, was invented, and that enabled, these are different increased intensities, and these regions here enabled different types of physics that are, you're entering different types of physical regimes. At the University of Michigan, we've been doing this kind of stuff for a long time. We had a previous laser called Hercules, and the one that is recently started operation is called ZEUS. The founder of our lab was Gerard Moreau. So for inventing chirped pulse amplification, which has had a lot of repercussions, both scientifically and also for applications, he won the Nobel Prize in 2018, along with his student Donna Strickland. And he came to the University of Michigan in 1988 or so, and founded QOS, which is the Center for Ultrafast Optical Science on North Campus, and that's been pretty much continuously funded by the National Science Foundation ever since that time. He started the development of the Hercules laser, which was about 300 terawatts, so about less than a petawatt, about a third of a petawatt. And so, like all French people do, when he retired, he went back to France. But we kept doing this stuff at the center, and he won the Nobel Prize in 2018, and then we renamed the center after Gerard. And so in 2023, the son of Hercules, ZEUS, we got funding for that. It's actually the other way around. ZEUS is actually the father of Hercules in Greek mythology. So that's a complicated explanation for that. However, it did seem to work with the whole Greek mythology theme. Gerard, this is actually an acronym as well. Gerard, there's a really nice statue of Hercules in the Louvre that he liked, and so he somehow made this actually into an acronym, but I can't remember what it is. But it is Hercules. So we kind of did the same for ZEUS. It is a little bit of a backronym, but and I'll tell you what it means. It has a little bit more connection to reality than the one for Hercules. Subsequently, so there's been a lot of work on, so Gerard and Donna won the Nobel Prize in 2018, but actually there's work also in getting even shorter pulses. So the world record for short pulses is something on the order of attoseconds now. So we can produce pulses which are 50 attoseconds, and an attosecond is 10 to the minus 18 seconds. So it's really, really short. The problem with that is you can't get so much energy. It's really hard to amplify an attosecond pulse, and we don't really know how to do it. However, the Nobel Prize was awarded for that, which kind of came along from the work that Gerard and Donna had done, and was won by Pierre Agostini, Ferenc Krauss, and Anne Willier just a year ago. And just for equal time, Pierre did quite a bit of work at Ohio State, so just give him credit for the last few years of his career. He was at Ohio State. So I did get a ChatGPT version of this for Ohio State. So I couldn't get Pierre to come, but I guess that's. I still think that's better. So I don't know your opinion, but in any case, there's a lot of good stuff going on at Ohio State. So subsequent to that, there has been a lot of this kind of area of trying to pack as much energy into a short pulse as you can has been going on around the world. And you can see in 2009, there were on the order of 30 or 40 10 terawatt systems. And 10 years later, there's now hundreds of these laser systems around the world. A lot in China, a lot in Asia, a lot in Europe, and fewer in the United States, even though the technology was developed in the United States. So there's a bit of an impulse for also working towards the frontier of this area in the United States. And so the highest power lasers in the world are part of a infrastructure program in Europe. There's 3 facilities called the Extreme Light Infrastructure in Eastern Europe, spent about €1 billion on building these multi-petawatt laser systems in Eastern Europe. And these are just starting to operate right now. And the highest power laser in the world is actually in Romania, operational right now, at 10 petawatts. So we're just trying to catch up with that. But you see this is a stadium-sized facility. So ZEUS. So ZEUS is an acronym. It stands for the Zettawatt Equivalent Ultra-Short Pulse Laser, Zettawatt Equivalent Ultra-Short Pulse Laser System. So it's designed to do experiments at the frontier of high intensity and produce very, very high powers. It's not a zettawatt. It's a zettawatt equivalent. Zettawatt is 10 to the 21 watts. I just said we had 10 to the 15 watts, petawatt scale. So am I lying? What does that mean? So there are experiments that we would like to do, which we can do in the laboratory because of the way our facility is constructed to enable science in this kind of zettawatt regime. So if I go back to this picture, you see that in this case, at low focused intensity, at low powers, this is atomic physics, so we're not ionizing anything. We're creating nonlinear effects perhaps in the materials. But once we reach a certain intensity, a certain field, we start ionizing. We make a plasma, and we reach this regime. As we increase the intensity even more, the plasma becomes relativistic. The particles in the plasma gain so much energy from the interaction that they gain mass, and then the dynamics and the physics is quite a bit different. And so basically what happens in a plasma, in this regime, you create a blob of high temperature material from ionizing it, and it expands in all directions. A relativistic plasma is basically a directional source. So you retain some of the momentum of the photons, and you start making beams of particles, beams of X-rays, and it's like doing mini accelerator science with these relativistic plasmas. As you crank up the intensity even further, all sorts of weird things start to happen. You actually are able to what's called boiling the vacuum. The intensity becomes so high that electrons and positrons just start emanating from the vacuum. And so that affects the dynamics of the plasma, that affects all the physics. In actuality, the criteria for producing electrons and positrons from the vacuum is actually up around here, 10 to the 28 watts per square centimeter. But we're not that. We're only down here at 10 to the 22 or 10 to the 23. So that's where we have this zettawatt equivalent. We're not a zettawatt, but we can arrange our experiment to reach this regime using the facilities that we have. And so basically, again, high intensity, where a petawatt laser produces 10 to the 22 watts per square centimeter, 10 to the 23, that intensity is like taking all of the sunlight incident onto the Earth and focusing it onto a human hair. And so the total sunlight incident on the Earth is about 100 petawatts. Again, that's CW, it's not pulsed. And if you focus it to a human hair, it's around 100 microns, you get equivalent intensities. But we want to get that intensity in the lab, but the equivalent of actually an even higher intensity. And we do that by using 2 beams. So one of our laser beams generates a relativistic interaction, generates a high energy electron beam moving almost the speed of light, and then we collide it with a super high intensity laser. And in the frame of the electron beam, the electric field looks like it is at that due to the zettawatts, so a zettawatt power or 10 to the 28 watts per square centimeter. It's called a Lorentz contraction. Okay, so in this really relativistic frame, whoops, I'll go back. In this really relativistic frame, we can do the experiments. We can generate electrons and positrons from the interaction of a 10 to the 22, 10 to the 23 watts per square centimeter beam with an energetic electron beam. However, again, people always ask me, can I use this for some terribly destructive purpose? And the answer, unfortunately or fortunately, is no. I can't make a Death Star. I can't destroy a planet using ZEUS. Basically, and that comes back to our pulsed versus continuous. So I don't know exactly how the Death Star works, but it seems to be a bunch of laser beams which are somehow combined and then go to the planet, bore a hole through the middle, and then it obviously blows up. But this needs to melt it. It needs to melt the planet in order to destroy its core. Presumably, I'm not exactly sure. Our laser doesn't have that much energy. And so it has, again, this flying pancake of light. And if it tries to travel even through air, its intensity is too high. It ionizes the air. It makes a plasma, and the plasma has all sorts of instabilities. So even taking our beam and taking it across this room is difficult. It's very damaging for your eyes, but you couldn't really propagate it into the wall and produce a lot of damage. Typically, so then we have to actually propagate it through vacuum systems, and we have to use vacuum beam lines to do it. There are other examples of this. You know, the Navy has lasers which shoot down drones, and this is a picture of a laser which is mounted on a ship. Again, it has to melt the outside of a drone, and it has to track the drone. So it has to put as much energy as it can, and then watch the drone move around and track it until it melts on the outside. So as an example of this, we have a laser here. This is a 1 watt ultraviolet laser. If I can turn it on. Okay, so this is not a pulsed laser. Okay, and let's see. You can see that? I'll turn this on, and the laser is it on? Yep. So there should be a little card there, which it's just heating it up. And okay. Okay, we should. Okay, so it happened faster than we thought it was. So it starts a little fire, burns a hole. So if this piece of paper was a drone, it would take a long time to pop it out. Or might as well do this. They have some balloons. That happened fast. Okay, so it works. But that's not that's the difference between a CW laser and a pulsed laser. So pulsed lasers, we don't actually even have and pulsed lasers are used for all sorts of applications. And one of the main applications is semiconductor manufacture. So you produce a pulse of light, you make a plasma, and you produce X-rays from that plasma, and then you collect those X-rays and irradiate a semiconductor. And so the tools that are used to make the most advanced chips are using laser-produced plasmas. Each one of these guys is around $100 million, and so there's only one company in the world that makes them, but these are kind of ubiquitous now, the standard for generating the most advanced computer chips. Similarly, we don't even have the most energy in a pulse laser. The biggest pulse laser in the world is called the National Ignition Facility. which is at Lawrence Livermore National Lab in California. And you see, this is it here. So this is 1 square mile at the National Lab. And if we zoom in, we can see it's a football stadium, and this cost many billions of dollars. And a football stadium with 3 fields or 2 soccer fields. And all that energy is focused into a spot, which is 1 millimeter. So this is used for experiments in nuclear fusion or for national security. This does not produce, so ZEUS is 10 times higher power than this, but 30,000 times lower energy. So we have a much, much shorter pulse, 1 million times shorter, which enables us to do a completely different regime of physics, mainly to do accelerator science and high field science, whereas this produces really high pressure plasmas, which can be used to compress material, basically, and drive fusion. So it's, again, on the order of a much larger facility that we have, but the technology is quite a bit different. So this is our lab on North Campus, and so this is only about 15,000 square feet. And so, however, it produces unique laser pulses and for science. And so, when we got the funding from the National Science Foundation, the university gave us about $10 million to renovate this whole lab space and actually chase away all the people who used to live here. I'm not sure where they went. But they're not there anymore. And now so this is where our laser is located. This is a clean room. And these are called the target areas. And so the way the experiments work are you separate the laser from where the interaction of the laser occur. And the clean room, this is an environment which is about 100 times less dust than a normal office, and that's required because of all the expensive optics that are used in the system. And again, it's not just one laser, it's many lasers all working together to produce this one ultra high power short burst of light. And then once the laser reaches its highest power, it can't travel through air anymore, okay? So it's too high power, it would ionize the air. And so it needs to travel through vacuum tubes that we evacuate the air from, and then that goes into, and also can't travel through windows, can't use lenses anymore because there's nonlinear effects in those optical materials. And then it goes into a place where we set up to do experiments. And there are 3 different areas where the experiments occur. And they're all surrounded by radiation shielding. So because the interactions basically produce beams, high energy beams of particles, the energies of the laser is transferred to the material, to the plasma, to the electrons and the ions in the material, and those have very high energies and then produce radiation. We need to shield it so someone walking down the hall doesn't get a dose. And it also limits our repetition rate of our system just in order to reduce the radiation. But again, don't worry, this is on North Campus. So during the pandemic, the university just demolished all the labs. It was really, I was really impressed that during the pandemic, we got all the building renovation done. Was pretty much gutted, the Gerstacker building on North Campus, and then we were putting these radiation bunkers for our experimental areas, and redid all the entire air handling system for the clean room. And now it was made into modern lab space. Again, building on the fact that we got this $20 million funding from the National Science Foundation in order to build this big upgrade of the Hercules laser. And so once it was finished in 2021, over a pretty short time scale, again, also quite impressive, we started filling it with optical equipment. Some parts of it were from our previous Hercules laser system, and other parts we purchased new and connected together. So it was done a little bit, we were trying to get as much out of the system as we could with the amount of money we had, so we used a lot of old components. We used components from different manufacturers and pieced them together ourselves. And again, here's the box diagram. It's not just one laser. The source of the laser, the mode lock laser that I talked about before, is right at the beginning, okay? And it uses, it doesn't use this material. This is neodymium doped glass, so it's neodymium atom in a substrate of glass. Our material is pretty unique in the world. It's titanium 3+, in a sapphire, in a crystal substrate. And the nice thing about titanium-doped sapphire is that titanium doesn't exactly fit into the host material, and so it has a lot of wavelengths that it can laze simultaneously. It has a broad spectral bandwidth. And so this is really the material of choice for producing really, really short pulses. So we're kind of limited using titanium-doped sapphire. It has good properties, and it has good thermal properties, but it also has bad properties which you can't energize it. You can't pump it with electrical current like I can with this laser here. I have to use another laser. I have to get the energy in really quickly because the population inversion, the fluorescence doesn't last for very long. So that really makes the system complicated and expensive. So each one of these green boxes is a laser that pumps an amplifier, and each one of these green boxes is around about $1 million. And so those guys pump our amplifiers, increase the energy of the pulse until to the point we put it into our experimental areas for doing some science. And then here's a picture of the titanium-doped sapphire crystal, which our largest one is about 17 centimeters in diameter. And again, there's only one company in the world that makes these, or can sort of make them. So here's just some pictures of the laser. Here's the front end of the laser, which is the oscillator, okay? And these are the amplifiers. There's John, who's sitting over here, aligning or unplugging this laser. I don't know what he's doing. And this is, again, a pump laser for the amplifiers. This is, again, from a French company. And we've had to purchase a number of these guys for the system, producing about 100 joules of energy to pump these amplifiers. And then we have a number of different vacuum systems throughout the system. Once the laser enters the compressor, everything has to be in vacuum because it is too high intensity, again, to propagate through air. In the experiments, again, here's the compressor chamber. It's a very, very large vacuum system in which we have 4 large compressors, 4 large compressor gratings, and then, again, these beam lines throughout the whole. The beam has to propagate through these beam lines. The beam itself is around 30 centimeters in diameter. And so the vacuum beam lines are all connected, and again, they have to be able to fit these very large beams, which can produce 3 petawatts. And so again, here's the outline. You can see the path of the laser, this red line. So it's a pretty circuitous path. The beam starts in the oscillator, then bounces through the different amplifier stages, picking up energy as it does so until it leaves the air and then goes into vacuum where it's compressed. And once it's compressed, then bounces around into doing an experiment. And so in the experimental areas, again, big vacuum chambers surrounded by a radiation shielding, because the electron beams that are produced on the order of 10 giga-electron volts, something that you would need in conventional technology, you would need a much larger system. Can't produce also radiation. Here's the diffraction grating. That guy looks a lot nicer than this one. And so this is, again, a $200,000 diffraction grating inside the chamber for ultimate of compressing these pulses. We also use things like, remember this is a flying pancake of light, and so the phase of the light has to be exactly uniform across the surface. And so to do that, because as it's being amplified and propagated, always little imperfections occur, we can correct those with a deformable mirror, a rubber mirror, or adaptive optic it's called. So you can control the shape of this mirror and make corrections for how the beam is propagated into the system. And so there's a total of 6 of these throughout the system. Again, expensive technology. And here's again, the size of the system means that the optics are very large. And then here's a deformable mirror with some of the different complicated alignment beams. And then to do the experiments, we use things like electron spectrometers at high energy. And here's a picture of the electron spectrometer in the petawatt chamber. We have different operational modes. We can produce 3 petawatts, that's the design goal, at 1 shot a minute, or higher repetition rate, 5 times a second, up to 500 terawatts, or we can combine those two to do this flagship kind of experiment where we generate an electron beam with one of the lasers, laser pulses, and then collide it with the high intensity beam to look at what's called nonlinear quantum electrodynamics, or boiling the vacuum and looking at some of these interesting exotic kind of physics. It's also important to do, I'll go back. It's important to do high repetition rate because in that case we can do lots of different kinds of experiments. The higher the repetition rate, you can use mechanisms like feedback and machine learning and artificial intelligence to actually control the actual shape of the laser pulse in, you can think of it as, instead of just a blob of light, as a 3-dimensional object that you can control by changing using our deformable mirror in real time to change what the spatial structure is. And we can also use other devices to control what the temporal structure is. So we can have a 3-dimensional blob of light, which we can control in all sorts of different ways, and we can use feedback to optimize things for improving our experiments and improving some of the applications. So it does work, and so here's a picture, a big shoe in Galena, 2 research scientists at ZEUS, and that's a picture of our amplified laser pulse. So to prove that it does exist, it is right here. So this is what's called a burn. So the laser pulse, before it's compressed, slams into this piece of photographic paper and you get a picture of the pulse and its intensity profile. Okay, so you see it's that looks actually, if you worked in this field for a long time, that's actually doesn't look too bad. However, you can see obviously it's got these things here. So our problem, so this is a 2 petawatt laser. So the thing is, we do have these lines in the middle. The issue with this is our very large crystal. We have the amplifying crystal is 17 centimeters. It has some imperfections in the middle. We're expecting a new crystal. We've ordered it 4 years ago, and they've finally been able to make it. Should arrive in June, which is a much higher quality, which won't have these lines in it. We should be able to crank it up to 3 petawatts pretty soon. So, to recap what I just said, turns out on North Campus, unlike here, we're right beside the School of Architecture. And School of Architecture has lots of students and who are really good with 3D design and drawing. So, and they also don't work for very much money. So we're fortunate to be able to show you what I just talked about. Maybe this is more instructive. You can see this is the laser pulse. It's been chirped, right? So it's stretched out in time. So it's about a nanosecond long. The music went away. Not super important. Let me coming back. Obviously, the light is actually traveling a lot faster than this. However, whoops, I'll go back. I missed that. Oops. Oh, sorry, I have to go. won't touch these buttons again. So this will just show you how the light propagates through the system. This is the amplifier. So every time it passes through this titanium doped sapphire crystal, its energy increases. These amplifying stages are being energized by these other lasers over here. So it's picking up energy. It's still chirped, right? So the red part is in front of the blue part, and the beam size is getting bigger. And then it goes to bigger and bigger amplifiers, taking energy from this crystal every time it passes through. So it's bouncing back and forth. And sometimes you can hear it. And in any case, the beam is split into two, so we do experiments. We just use a beam splitter. Part of it goes off to a separate stage, and the 3 petawatt beam continues on its own. This mirror here is not hanging in space in reality. So now it's amplified to its full power, and it goes into the compressor chamber. So now it enters vacuum, never sees air again, because this is the point where we squeeze the pulse into a much shorter time. We compress it by about 100,000 times, and it's really kind of stuck there. But so you see the different frequencies traveling at different speeds with different distances, and now it's compressed to 25 femtoseconds, and that's the thing we want to do our experiments with. And then it propagates into this beam line and goes into the experimental area. Okay, we'll follow the pulse as it travels through this vacuum beam line into what we imaginatively called target area 1. This is a 2.5 petawatt pulse, and it interacts in the chamber with the target, which is a cell of gas, produces a plasma. The interaction of the light with that plasma, here's a numerical simulation. The laser pulse generates what's called a plasma wake, and that plasma wake has electric fields in the direction of laser propagation, so it can accelerate those electrons and produce a multi-GeV electron beam. And so that's this little guy. We can watch him. We're almost finished here. We can watch him go through a plasma lens to focus the electron beam, and then collide with this other laser pulse, which is just designed to exactly be coincident. And in this case, during the collision, we're generating these electron-positron plasmas, and producing all sorts of interesting physics and to be measured. So this is the design. So again, John and Anatoly with animation from students as well. And so this was opened about in October 2023, and Gerard, our founder of the lab, came, and also importantly the National Science Foundation folks came as well. Hopefully they're still employed, and but we're in operational mode now. We're a user facility, so we're an international user facility. We have users coming from around the world to use ZEUS and producing a broad range of potential experiments. It's designed mainly to do hands-on training, and the operational goals are for science, and training graduate students and postdocs, and so mostly academic users, but also international academic users, and people from the national labs and industry are also welcome. So we've just finished the first year of operation, and our first experiments were actually two groups from the UK, both led by women scientists, Kate Lancaster and Eva Loss, 2 successful experiments looking at fundamental science using ZEUS. And there's pictures of their experiments. And just towards the end, what are the things we're going to look at? Again, this is a relativistic temperature, so we're mainly producing plasmas with, which can produce directional energy, directional beams of particles and radiation, and very high energy electron beams, huge magnetic fields, and again, studying of quantum electrodynamic effects. However, this is a user facility, so even though the University of Michigan has a certain amount of time on its own, we're also going to stage any experiments that get through the proposal review panel that are deemed worthy enough of the science. And so it's the National Science Foundation really just wants us to have a wide range of different scientific experiments as possible, and also to grow the community and to grow the use of this facility. So again, but fundamentally, it's mostly plasmas, okay? So you have these strong intermolecular bonds with solids, liquids, and gases, but once the temperature becomes high enough, everything becomes disassociated, and you get two fluids, a fluid of electrons and a fluid of ions. It doesn't occur so much in, I might as well turn these on. So these are plasmas. It doesn't occur so much in where we are, but there occurs in electrical discharges and lightning, and again, in really kind of exotic places in Earth. However, we only live in this cold, dark corner of the universe here, and this is number of particles, this is density, and this is temperature. And so in this region where things are dense and cold, like on Earth, solids and liquids and gases exist. However, for the rest of the universe, 99% of the visible universe is made of plasmas. And so the rest, so again, 30 orders of magnitude in density here and 6 or 7 orders of magnitude in temperature. All the rest is regions where plasma physics is the dominant, whether it's the solar corona, the magnetosphere, and laboratory experiments like in fusion. And our experiments, we're way up on the left corner around here, probably more in this, right on the top where we have relativistic plasmas. And again, fundamentally, it's generating plasma waves. The plasmas are collective phenomena. It's like two fluids, a fluid of electrons and a fluid of ions interacting with each other. And so you have all the fluid dynamics of liquids, but now it's a charged fluid. And so it becomes more complicated. You have coherent effects and collective effects, and so it makes lots of electric fields and magnetic fields. So applications, again, are mostly from particle acceleration, from radiation sources, making compact particle acceleration, particles, making compact sources of electrons and X-rays and gamma rays, muons, positrons. We've made pions. There's a whole range of interesting kind of radiation sources and particle beam sources, accelerator sources, and anything that you can potentially, applications you can do with conventional accelerators, you can also do with laser-generated accelerators. We're approaching the point where we can produce beams which are similar in energy to the Stanford Linear Accelerator Center, which used to operate at up to 100 GeV. And applications are for using these sources of particles to make X-rays. Here's some images of super high resolution X-ray images using a laser accelerator source. This is a mouse embryo doing a three-dimensional tomographic image or looking at the structure of bone. So lots of potential applications, scientific, medical applications, and again, things for semiconductor applications, for homeland security, making all sorts of particles. So it's fundamental science and applications all together. In addition, you can go to other parts of the universe. We make these weird relativistic plasmas that occur in different places, large magnetic fields, looking at supernovas, looking at the origins of cosmic rays, the plasmas that we generate with lasers. We can look at the dynamics of these magnetic fields, which are connected to solar flares or coronal mass ejections, looking how cosmic rays are generated by colliding magnetic fields, or looking at imaging things like hydrodynamic instabilities that occur in supernova. So there's a lot of variety of different experiments that are possible and that we've started doing at ZEUS. And then even other regimes using nuclear interactions at very high power. So now we can actually use lasers to do nuclear physics to excite nuclear transitions and to do other kind of interesting science. So here's just an image of a laser heating a material and all the nuclear reactions that are occurring. Once you generate these energetic electrons and then produce very energetic X-rays and gamma rays to produce excited nuclear states. So I'm going to stop there. And so these are the whole team that helped me with various slides in the presentation, and also have been able to make ZEUS to work. And I will be happy to take any questions.
Thank you very much, Karl. We are bringing microphones out for the people in the audience who have questions. And so line up behind a microphone if you have a question. We'll just take a minute to let things settle down here. We have questions from online. I guess we have a microphone over here. Okay, go ahead. And please get close to the microphone so that also people online can hear.
Presumably you don't have unlimited budget, so my question was, both in the design of the facility and the experiments that you run, how do you measure the bang for the buck on deployment of the capital and the building?
So NSF is very concerned about doing that. So we track the number of users that we have, the number of different institutions that use the facility, and I think for our first year we had somewhat over like 120 users with like 20 different institutions come use the facility. So NSF really wants us to maximize the output. At the end of the day, our output will be science, and so the number of papers that are produced, the kind of quality of those papers, the impact of those scientific papers, and so we track those as well. We're still in the, after 1 year, we haven't had so many papers produced from the users yet, but that's kind of the goal. So.
Just to follow on is more in terms of you have such a wide variety of potential experiments. How do you decide in what order to do them and which to do and which not to do?
Oh, so we have a completely external proposal review panel. So actually, our window for accepting proposals will be closing soon. So you have a good idea, you can submit a proposal via our website, and then those proposals go to the panel, which has no representative from the University of Michigan. So what they do is they look through all the proposals and adjudicate them and rank them, and then they send them back to us. And the ones that are technically feasible, we'll schedule them kind of in rank order. So NSF really wants, they're interested in expanding the field of study. So they want people who, maybe who people don't do stuff that I do, like high power laser accelerators, but also they want people to use the facility for doing that and to expand the impact of the facility. So that's their goal. They want more and more users to kind of press us to have shorter experiments, more people coming in and out as well. So, and we're trying to accommodate that.
We're going to follow that up with a question, which is, how long does an experiment take? So you mentioned shorter and longer, but generally, or how many experiments do you anticipate doing in a year?
For the first year, it was a ramp-up year. So we had 6 experiments with multi-institutional groups, and they were 4 weeks long. And so this year we're having more experiments, and some of them are 2 weeks long. And we've had an experiment which was just 1 day long. So it really depends on what they want to do. So if you just if you want to do a very complicated experiment where you're aligning multiple beams and a complicated diagnostic you're bringing in, it may take longer time scale. But if you just want to take an object and image it with our X-rays and do a super high resolution X-ray imaging, we can do that all in a day. So it really depends on the different kind of request. Again, NSF wants us to cycle people in as much like a X-ray synchrotron facility. We're not exactly like that, but we want to be able to offer different modes of operation.
Do the experimenters bring their data acquisition and everything, their detectors and all that, or do you have those in place, which kind of constrains the kind of experiments, it would seem?
We have a whole bunch of spectrometers and particle spectrometers and diagnostic equipment. However, people can also bring their own stuff in, and so that's encouraged. And so I know there's some crazy proposals for bringing weird stuff in to try to do an experiment with. I don't know if we'll be able to. So, it really is a combination of the two. And so also, we try to develop diagnostic capability. I didn't talk about it. Some of these things involve targets. So you have to hit something with the laser. And so we have a target fabrication lab. That's another critical part of the technology. Can we actually make something interesting that people want to shoot or to want to image? And this is all kind of developing area over the years. But we've had lots of experience in this over the past 30 years doing this stuff.
Thank you for the presentation, very interesting. My question is very simple. Do you use optical simulation software to design your experiments?
So there's different types of software for actually designing the laser system as well. So we do have some in-house software for designing the amplification of the laser pulses and to do ray tracing, which is kind of commercial software we use for tracing the pulse through the different optical elements. For the plasma physics, it's completely different, and so those are really large numerical simulation codes, typically ones that you can run small versions or on a PC or production runs on a supercomputer, and those things we have access for as well. So we use techniques like fluid simulations for some of the dynamics, or what are called kinetic simulations, where you track all the particles individually, like particle and cell simulations. So we don't necessarily provide that service for the users, but we can in sort of a collaborative mode. But a lot of these codes, they're not proprietary, they're open source, and so people do have access to using these things. Just for most of the big codes, you don't really need to buy something. You just need to collaborate with some other group. So this is part of the scientific the way the science works in this field.
Here's an online question about, is this laser upgradable as time goes on, technology goes on, or are you pretty much committed to the way it is?
No. So there are lots of ideas. Our limit. So we have 1 shot a minute with our 3 petawatt beam. So, which is limited by our pump lasers. It's not limited by our amplification medium. So theoretically, we can operate at a higher repetition rate, and so that enables us to get more data. It'd be nice to be able to operate at 3 petawatts at a kilohertz. So, however, 3 petawatts at a kilohertz would make so much radiation, I don't know what we would do. We would have to, that may be the one of the limitations. It's a limitation on our repetition rate now is our radiation. We're not really approaching that, but if we're going to increase the number of shots, then we will have to think about kind of limiting the high intensity shots, the electron beams that we're producing. It's also possible to go to higher powers, and typically for a laser, the more energy, the bigger the footprint of the lab is, like I showed from the National Ignition Facility. But we can make the pulse shorter. We can go to a few femtoseconds, and for the same amount of energy, we would increase the power. So we're not really fixed in stone necessarily.
I'm curious what the input power looks like for a single shot.
Input power is very high, so it's not very efficient. So typically, so the electricity comes from the wall, goes to the pump laser, and that is probably 5% efficient. So, and then we pump our amplifiers, which might be 50% efficient, and then transmission through the whole system might be another 50%. So, it's a couple percent of wall plug efficiency into the final output pulse. And you store that from capacitor banks or something like that. However, we're not, even though we're running at multiple petawatts, and even though the power grid in the U.S. is only a terawatt, when we fire, the lights don't flicker on and off, right? We're storing the energy and then.
Okay, so I can't blame you.
Yeah.
What about how good does the vacuum need to be? I mean, I would think that at some point, any sort of air molecule floating around interacting with this laser would be bad. So how good does that vacuum need to be?
Yeah, so it depends on the kind of experiment we want. So typical vacuums are, 7 orders of magnitude less than the air in this room. So that's a pretty good vacuum. But there's still lots of molecules floating around at that point. So it really kind of depends on the type of experiment. So it also, the nonlinear interaction of the beam as it propagates through the air, through anything, will ionize the material. But the density of the material of the gas determines the kind of collective effect, the self-focusing of the beam, and that's really what kills us. So we can't propagate it through a solid material, but if we reduce the density by 10 orders of magnitude, even though there's lots of molecules still there, we won't cause self-focusing or catastrophic damage to the laser beam. So it really just depends on the particular situation. So it's not an ultra high vacuum. I wouldn't say it's a high vacuum, but not an ultra high vacuum that you might need in the semiconductor industry or something like that.
I can check that question off the list of online questions. So there are some technical questions, but following up on that, maybe just a little bit in terms of so you showed the movie, and I tried to figure out how long it took. But how long does it actually take to build up the energy in a pulse?
In the path of the laser?
Is it really just the time that it takes light to travel the entire, whatever, half mile?
So what happens is our pump laser has a pump which has a pulse which is maybe 10 nanoseconds long. So it puts its energy into the amplifier, and then that has gain for about 3 microseconds. So, and then we have to bounce our beam and extract that energy from that amplifier during those 3 microseconds. And so, so the time scale, so you energize the amplifier, then you have to pull it out before the fluorescence of the amplifier goes away. And so, the total path of the beam as it bounces many times through the various amplifiers is hundreds of nanoseconds. So, many nanoseconds in duration. And so the limitation, again, of this technology is, that 3 microsecond fluorescence time. It's really, really short. It would be really nice if we could continually pump the thing, and so we don't have to use these $1 million pump lasers in order to energize our amplifiers. So it would make everything simpler. So that's another possible improvement in the technology, which increased the repetition rate, is using a different amplifier material, a different wavelength, and things like that. So
It's still going to be light that puts energy in the amplifiers.
potentially, I mean, with the diode laser uses electricity, but basically, or flash lamps, things like that.
Flash lamps.
Which is how
The YAGs work.
how this guy works. Would have flash lamps surrounding it to excite the phosphate glass.
Another pretty technical question about the mode locking, whether you have to do anything special. Is there some kind of modulator that keeps the modes in sync?
That's right. So you have to modulate the. So there's a box there that I put in the thing. So you do have to modulate the transmission of the light at exactly the right frequency in order so all the modes will be synced up together. And so typically, if you don't do that, one particular frequency takes over. It produces a single very narrow bandwidth pulse. So if you need the mode locker to keep the bandwidth large, to have all these frequencies actually lasing at the same time and adding coherently to produce a pulse rather than a continuous stream of garbagey photons, which are still laser, but it's not a useful pulse laser.
So what is it about lasers that makes that effective? Is that compared to bullets, I guess?
Why you would, well, I mean, they're cheap, right? So relatively, I mean, the light is, once you've made the thing, then you can, then it will work. And so you don't have, provides it's cheaper than a missile, obviously, and also runs pretty much continuously. I'm not an expert in laser weapons, but all I know is ZEUS is not cheap, and it doesn't work very well shooting down drones. Typically because as it propagates through air, it doesn't maintain its intensity, doesn't maintain its integrity. As it propagates, the nonlinear behavior of the air molecules at atmospheric density causes it to self-focus, and so you get a huge bunch of small filaments of light. So it's not one coherent laser beam, it's a bunch of filaments which don't really work very well for long-range deposition of energy. You can use these things for like remote sensing, or you can, ZEUS would happily work, in the stratosphere where the density is lower, but I don't really want to launch a ZEUS into the upper atmosphere, but those are other possible things.
Yes.
So 2 questions. One is, it's a fairly unique instrument, device, laser, to when you are looking at doing, getting quantitative results out of it. How do you measure the intensities or the energies that you're producing? We're talking about pulses in the 100 joule amplifiers, and those are measured somehow, but then the resulting pulse that comes through into the sample chamber, how do you know the energy of that pulse or the power that you're emitting?
So I mean, that's a super question. So I mean, it's not so hard to measure the energy. I mean, you just do this and put an energy meter or calorimeter and to measure the total amount of energy. That doesn't say what the pulse duration is. So to measure the power, you need to measure the total energy and the pulse duration at the same time. And then to measure the peak intensity, you have to measure the focal spot at the same time. And at the same time is a big problem. So the typical way of measuring short pulse is these pulses are the shortest thing that human technology can devise. So I don't have a camera that obviously works in the femtoseconds. So you have to split the beam into 2 parts and then and then collide it with itself and looking at a nonlinear interaction. It's called an autocorrelation. And from that, you can measure the pulse duration by have an autocorrelation with two parts of the same pulse and looking at a nonlinear effect induced by the two parts of the pulse. However, that doesn't really work at 3 petawatts. And so at 3 petawatts, after we've amplified it and we have a really short pulse, then how do we know, and we try to focus it, how do we know really what the intensity is in the focal spot area? It's easy enough at lower power in the same system to kind of measure it, but at super high power, so that's really an experiment. So we use physics. We do look at a physics phenomenon. We do like really interactions at very low density and looking at ionization states that can be produced in a very, very, very low density gas. Try to measure those and try to correlate them. But that's kind of an active area of research. So how do you absolutely confirm that you have 10 to the 23? So it's kind of it's kind of a regime where there's no conventional way of doing it. So you have to do an experiment, and if that agrees with the kind of the theory and the simulations and the modeling, then you're kind of confident that that's the intensities that you have.
As sort of the second question is related, how do you synchronize? So you're talking about a seed pulse. There's a nanosecond pulse that's a single seed pulse, but then the repetition rate of the entire device is single pulses per minute. So your amplification stages, or the lasers that are pumping the amplifiers are producing, you said, a 3 microsecond pulse, and synchronizing that single nanosecond pulse with those amplification stages. Is this a train of pulses that then results in a 1 minute, rep rate, or is it that this all has an elaborate synchronization?
It all has an elaborate synchronization, I guess. But that was a good question. So I kind of glossed over that. So the oscillator doesn't produce just one pulse. It produces a train of pulses at, say, 50 megahertz. So they're separated by nanoseconds, a foot per nanosecond. But you can optically switch out one of those pulses, and then just amplify that one single guy. And you can amplify it at 10 hertz or 50 hertz, or 1 shot a minute if you want. And so typically that's what we'll do. We'll have an optical switch, which uses a nonlinear crystal, which takes one of the pulses from the train and amplifies that one. And then the timing is not so hard because microsecond timing is not hard for triggering the lasers, for pumping the other lasers. And if we want to synchronize things which are a femtosecond apart, that is really hard. Because again, that's, a femtosecond is 300 nanometers. And so the only way really to do that is synchronize it with itself. Like I talked about autocorrelation, you have to split the beam into 2, and then you can, because of the exact path length, you know exactly what the difference in timing is, and so you can synchronize things on that scale. But the amplification's not so bad because the timescales for the fluorescence and the gain and the pumping are longer than the pulse duration that you're trying to amplify. If that's kind of an answer.
Okay, great. Well, with that, I think we should thank Professor Karl Krushelnick again for a great presentation.